Well, we've been using the chain rule as it applies in situations where we have an expression raised to a power, and that we use the general power rule version of the chain rule. And we've just looked at finding the derivative of trig functions where the argument is something other than x, and the way we apply the chain rule there. Like, for instance, how do we find the derivative sine of 3x minus 1? Well, we have the same situation with exponential functions. We've accepted, we've been given the information that the derivative of e to the x is just e to the x, which is very special in its own way. But we haven't dealt with how do we find the derivative of e to a power other than x, like e to the 4x, or e to the 3x squared plus 4, or even the derivative of e to the negative x. All of these require something a little different before we can find the derivative, and I'm sure you've guessed it, that we're going to have to use the chain rule to find the derivative of functions where we have e to a power other than simply x. Even negative x, we have to use the chain rule. Well, as we started in earlier examples, let's remember the chain rule. It's about the derivative of a composition. And remember, the derivative of v of an inside function is v prime of that same inside function, then times the derivative of the inside function. So I'm going to set things up where our v is e to the x, and our inside function u is 3x squared plus 5x. And so if I evaluate v at u of x, that means I'm replacing this x with 3x squared plus 5x. And if I replace this x with 3x squared plus 5x, then I replace this x with 3x squared plus 5x. So we have a function f that is e to a power other than simply x. And this is the kind of situation we've been discussing. So we want to know how to find the derivative. Well, we've got the formula, and the formula requires that we know v prime. Well, if v is e to the x, then v prime is e to the x also. And we need to know v prime evaluated at the inside function u, so v prime evaluated at u is v prime evaluated at 3x squared plus 5x. So once again, if we replace this x with something else, then this exponent is replaced with the same thing, and so v prime happens to be 3x squared plus 5x. And of course we need u prime. In u prime, we can look here, that's simply the derivative of 3x squared plus 5x, which of course is 6x plus 5. Well, now we're set for the derivative then of f, because the derivative of f says evaluate v prime at u. Well, that's e to the 3x squared plus 5x, which we have written here. Okay, there that is. Here we have that. Times the derivative of u. Well, the derivative of u is 6x plus 5. And so here's our result. Now it's more useful to look at what we started with. So here's the original function that we started with. Let's look. F of x is equal to e to the power 3x squared plus 5. And when we found the derivative, we have e to exactly the same power, but here we have the derivative of that power, which we called u. So this is like f of x is equal to e to some power other than x. And the derivative then is e to that same power, okay, times the derivative of the power. I have that formalized here in this next slide. It says that very well and concisely. The derivative of e to a power is equal to e to the same power times the derivative of the power. So let's use this information to do an example. Here we're asked to find the derivative of e to the 2x plus 1. That is, f of x is e to the 2x plus 1. We're asked to find f prime. So as we just learned, to find the derivative in a case like this, The derivative of e to a power is e to exactly the same power, so e to the power 2x plus 1, but the thing we have to remember is then we multiply that expression with the derivative of the power itself. Now, I know we could have done that in our head, but I want us to get used to this idea, follow up with a derivative. And of course here, the derivative of 2x plus 1 is just 2, so we'd say, okay, e to the power 2x plus 1 times the resulting derivative, which is 2. 2. But of course, we'll usually write this factor 2 in front, so we'll write this as 2 times e to the power 2x plus 1. And that would be our final answer. Okay, well, let's look at an additional example. In fact, there's several examples I want to look at. Here we have, we're asked to find dy dx if we know that y is equal to e to the power negative 3 divided by x. We've been through, we see that this is very easy to do, except that we're going to run into a little obstacle here, and we'll deal with that as we come to it. So if this is y, then we simply have y is e to a power, and so to find the derivative of y with respect to x, it's exactly e to the same power, so it's e to the power negative 3 divided by x. But the part we cannot forget, be very careful, is then we have to multiply with the derivative of the exponent, and the exponent here is negative 3 divided by x. So this is the part that we always need to remember to do when we have e to a power. Now, this derivative we can't necessarily do in our head, and that's the reason it's critical to be able to write down our problem in this fashion. So what I'm going to do is come over here to the side and work on calculating this derivative that I've got. So this derivative of negative 3 over x. So the derivative of negative 3 over x, well, the first thing I want to remember is that this is not in a form that's easy for me to differentiate. Rather than use the quotient rule, which I could, it would be a little easier to rewrite my expression as negative 3, let's say 3, times x to the power negative 1. And then that derivative is easy to calculate. So to find the derivative of negative 3 times x to the power negative 1, I'll say negative 1 times negative 3, which becomes positive x to a power 1 less than negative 1. Well, negative 1 subtract 1, of course, is negative 2. And then we recognize that we wouldn't write that as x to the negative 2. We would leave our form as 3 times 1 over x squared, which becomes 3 divided by x squared. And so now we're going to replace this derivative with the result that we had here. Let's come back to do that. So now we have e to the power negative 3 divided by x times the resulting derivative of the power itself, which was 3 divided by x squared. Now we have two expressions multiplied together that we can easily do the multiplication. And in this case, we'll have a denominator of x squared, because after all, this is over 1. We can imagine that. And we have e to this power times 3. We'll write the factor of 3 in front, so we'll say 3 times e to the power negative 3 divided by x. Now, this was an example where it was almost critical for us to be able to write this step as a derivative, take the derivative step, because that took a little bit of work for us to complete. Okay, well, in this next problem, we're asked to differentiate y is equal to e to the, y is equal to 4 times e to the power negative x. And, of course, we might recognize quickly, well, let's get started, but we might recognize quickly that we actually have a constant times a function. And so when we're going to go about finding the derivative of a constant times a function, that is, we're going to find dy dx, which is the derivative of this, well, that's the constant times the derivative of the function. So the constant 4 times the derivative of e to the negative x. Whoops. Now, our concentration becomes on finding this derivative, and it's a common error made is just to say that this is e to the negative x. But remember that the only time we get exactly the same thing, the only time we do not apply the quotient rule when we're taking the chain rule when we're taking the derivative of e to a power, is if our power is exactly x, and here our power is not exactly x, so the chain rule has to apply. Well, here's our 4. Now, to take the derivative of e to the power, it's e to the same power, so it's e to the power negative x, but then we have to multiply with the derivative of the power itself. Okay? And in this case, that's the derivative of negative x, since that's the power. But we know the derivative of negative x is nothing more than negative 1, and so we have 4 times e to the power negative x times our resulting derivative of the power, which is negative 1, and then we'll simply rearrange. We have 4 times negative 1, we'll write that as negative 4, e to the power negative x. So this required using the constant multiple rule in the beginning and then the chain rule on e to the power negative x. Well, this is an interesting problem. G of x is x times e to the 2x power. Now we have to be careful in order to find the derivative. Well, we have to be careful and notice that in this example we actually have a product of two functions. First function is x, the second function is e to the 2x. So to find this derivative, we've got to use the product rule. So in using the product rule, we say first function times derivative of second plus second function, here we go, times derivative of first. And we can do these calculations, or at least some of them, very easily. Here we have the first function. Now, here we have the derivative of e to the 2x, which requires the chain rule since our exponent is not just x. So it's e to exactly the same power times the derivative of the power. And this is simple enough, I'm just going to think the derivative of the power 2x is simply 2. That's the derivative of the power 2x. And of course over here we have e to the 2x times the derivative of x, that was the first function, which is simply 1. And now we can go in here and we can see our result. We have a factor of x, a factor of 2. We'll write that as 2x in front. And then we have e to the power 2x. And finally we have plus just e to the 2x in this position or for this term. Now actually, this answer is acceptable. There's not any reason that we shouldn't leave this answer. Sometimes a book or sometimes a teacher will want you to factor, and as I've mentioned before, factoring is not just a means doesn't always mean simpler, but we usually factor with a means in mind. There's some purpose in mind. But for this example, just as an alternative answer, recognize that e to the 2x appears in both terms. And so we could factor out e to the 2x. And if we do, I'm going to factor it out to the right. So that means I'm going to have left in parentheses, whoops, well, this doesn't like me very much. Let's take care of that. Okay, and let's go back to, okay, let's factor out our e to the 2x, so that will leave a 2x and then a plus 1 in the second position times e to the 2x. Yes, that would be the same. So we could leave either one of these answers. That would certainly, either one would be acceptable. Well, here's another example, and one of the points I'm trying to make with these examples is that now we know how to take the derivative of e to the powers other than x. We have all the same issues that we've always had. We can be asked to find the derivative of a product of functions, find the derivative of a quotient of functions as we have here, find the derivative of, or find the slope of a tangent line or the equation of a tangent line when we have involved e to powers other than x. But let's get started in this example. Here we have, we're to find the derivative of y, where y is the quotient x squared plus 3 e to the 3x power, all divided by 1 plus e to the x. And so clearly we have to use the quotient rule. So as we remember the quotient rule, let's see, the derivative of y with respect to x in this case is going to be equal to, it's, as I recall, it's a long fraction because the numerator has a lot of parts to it, doesn't it? So what do? We take the denominator, which is 1 plus e to the x, and we multiply that with the derivative of the numerator. Well, here we go, the derivative of the numerator. Since it's pretty complicated, I'm going to just write derivative of numerator. And then we subtract. Okay, what do we subtract? Oh, then we reverse that, don't we? We take the numerator which is x squared plus e to the 3x, and we multiply that with the derivative of the denominator. And although I made that division bar long, I didn't make it long enough, did I? And then we divide that by the original denominator squared. So there's our first step. Now, we're going to run into a few issues here because finding this derivative isn't going to be particularly easy. So let's get started on our next line. Once again, let me draw the division bar. Maybe I'll make it a little longer this time. Okay, so we still have this 1 plus e to the x in this first position. And then we have this derivative to deal with. Well, this derivative is going to have a couple of parts. This is a sum, and so we'll take the derivative of x squared plus the derivative of e to the 3x. And so we need something here to say that we're going to have several terms here, and so I'm going to write it in brackets. Well, the derivative of x squared we can easily do. That's simply 2x. But then we have to say plus the derivative of e to the 3x. Now, finding the derivative of e to the 3x is having to use the chain rule again. And remember, the derivative of e to the of a power is e to the same power, but then times the derivative of the power. And in this case, the derivative of the power 3x is simply 3. So that's the derivative of that power. So this result, which we can clean up here in a moment, is the derivative of x squared plus e to the 3x. And then, of course, over here we have minus x squared plus e to the 3x times the derivative of 1 plus e to the x. Well, the derivative of, this is a sum again, so we take the derivative of each term. The derivative of 1, of course, is just 0, but the derivative of e to the x, oh, well, that doesn't require the chain rule, does it? That's just e to the x. And then, of course, we have all that divided by 1 plus e to the x, the quantity squared. Now, I'm going to go in and see if I can't straighten up what I've got in here before I take the next step. So it's awfully messy looking, and I'd like to clean it up so that it's not so messy looking. So I have my 1 plus e to the x, and in these brackets, which I'm going to change to parentheses, I have a 2x, and then of course this is just 3 times e to the 3x. Looks a little better. And then minus, here I have x squared plus e to the 3x. And I think what I'll do is, rather than write this e to the x at the end, usually the monomial portions, factors, we write in the beginning. So I'm going to write it right there. And of course, again, that's all over 1 plus e to the x, the quantity squared. Now, I've seen many mistakes made by saying, oh, here's a 1 plus e to the x, and here's 1 plus e to the x squared. I can cancel those. But of course, most of us remember, and we're not going to make that mistake, this 1 plus e to the x is not a factor of the numerator. Before we can do any canceling, we would have to have the numerator in factored form, and it is not. So that's not an option for us. Now, what is an option for us is to take that numerator and expand and see if we can simplify. That is, do the multiplication we have here and do the multiplication we have here and see if we can combine some like terms. So we'll get ready for that. Here we go. Now, I'm going to do this and show the result here. Just a moment. Okay, I've done this multiplication. Let me show you what I did. I expanded the product of these two binomials. 1 times 2x is 2x. 1 times 3e to the 3x is 3e to the 3x. And then I had e to the x times 2x, which I wrote as 2x e to the x. Now here's the part I want you to look at. I multiplied e to the x and 3e to the 3x, and the result I got was 3e to the 4x. Well, why? Okay, well look what happens when I multiply, for instance, x to the second times x to the third. What do? We add the two exponents. Well, here the bases are both e, and so when I multiply e to a power times e to the power, it will be e to a power where I add the exponents. So the exponent x plus the exponent 3x is 4x. So that's how I got 3e to the 4x here. And over in this situation, I have negative e to the x times x squared, which I wrote as negative x squared e to the x, and then negative e to the x times e to the 3x in this case. Well, that's negative, but when I add those exponents together, x plus 3x, I get an exponent of 4x. And then, of course, our old denominator. Now, when we look at this, I think there are some places, some places where we might actually be able to do some combinations and some simplification. And where I'm looking right now is that I have a constant coefficient times e to the 4x and a constant coefficient times e to the 4x. And those are the only things that I see that are really alike that have constant coefficients. And so I'm going to combine those. Let's see let me get my division bar here. So I have this 2x, and I have this 3e to the 3x, and I have this, let's see, 3 minus 1 e to the 4x, so that's plus 2 e to the 4x. And then I have this plus 2x e to the simply x, and then finally minus x squared e to the x, all divided by 1 plus e to the x, the quantity squared. And in this case, I see nothing else that I can do to simplify. Although it's a complicated answer, it was a complicated function. So we're finished with this derivative. Before we go on, I'd like to look at finding this derivative, and specifically because this derivative requires us to use the chain rule in a couple of ways, and actually the chain rule in succession. We have to use it twice. So here we go to find the derivative of y with respect to x, dy dx. Now what we have to recognize here is that we're finding the derivative of sine. Let's not focus so much on what's inside. We're asked to find the derivative of a sine function. So to find the derivative of the sine function, it's the cosine of exactly the same argument, isn't it? So it's going to be the cosine of e to the power 3x squared. But if this isn't just an x in here, then we have to remember that we use the chain rule, and so we have to multiply by the derivative of the argument, the derivative of the inside. So in this case, we have to multiply with the derivative of e to the power 3x squared. Well, because we're so adept now at writing this part down, this makes it easy to step through, because we know to find this derivative requires us to use the chain rule as it applies to exponential functions. So let's write down the first part again. We have the cosine of e to the power 3x squared, then times the derivative of e to a power. Now if that power is not simply x, as we said, the chain rule applies, but it's e to exactly the same power, so e to the power 3x squared, times the derivative of the power. Well, let's see. I think this is simple enough that we don't actually need to write down derivative form. What is the derivative of 3x squared? Oh, that's simply 6x. So e to a power times the derivative of the power. Now we see that we have a string that we can clean up a little bit. We'll rearrange it. We usually put these factors in front, so I'll start with the 6x times the e to the power, that is e to the power 3x squared, and then finally the cosine of e to the power 3x squared. And we've completed what looked like a very difficult problem, but because we can write down our steps, this ended up being a very reasonable problem for us. Well, we've been finding derivatives of e to powers. What about bases other than e, that is, some other number to a power? So we know how to find the derivative of e to the 3x. We use the chain rule, or e to the negative x, we use the chain rule, or e to a power 5x squared plus x, we use the chain rule. But how do we find the derivative of 5 to the 3x power, or for that matter, just 5 to the x power, or 4 to the negative x power, or for that matter, the derivative of just 4 to the x, and so on? How do we find the derivative of 7 to the power 5x squared plus x? Well, we haven't discussed that yet, and we need to do a little bit of work before we know how to find these derivatives. But more generally, how do we find the derivative of some constant to a power that is a function of x? It may be simply x, or it may be something more complicated. Well, before we answer this question, how do we find these derivatives, we need to remember a little bit of information from algebra, and that is specifically that a constant raised to the power log of m base a. So the logarithm is base a matches this constant here, is simply equal to m. Now maybe you've forgotten that, and that's not surprising if you have, so let me give a quick explanation of why this is the case. Let's consider a to the power log of m base a. Let's temporarily call this exponent n. Okay, so the exponent log of m base a we're calling n, and so what we have here then is actually a to the n power, since n represents this exponent. Well, by the way, what this means when we see this, that if n is equal to the log of m base a, that means this base a to that power n is equal to that number m, and that's really what I've written here. And now we go back and say, okay, well, a to the n, and n is nothing more than the log of m base a to the n then must be equal to m. And I know this seems like smoke and mirrors or double talk, but this is actually a good explanation or a good demonstration of why a to the power log of m base a is equal to m. It's equal to the argument of this logarithm. Another way to think of this, by the way, is that this logarithm represents the exponent that we have to put on this base to get the number that's right here. So what we're doing is we're actually putting this exponent on the base a, so we better in fact get m. Well, more specifically, the way we're going to use this is that if we have e raised to a power that's natural log of m, we simply just get m. We just get the argument of the logarithm here that is in our exponent. So that's really the way we're going to use it. So let's look at a specific example. Suppose we wanted to know, for instance, the derivative of 5 to the x power. Let's just use this as an example. Well, from the discussion we've just had, then I can replace 5 to the x power with e raised to the power natural log of 5 to the x power. Because after all, e to the natural log of something is just that something. That's what we've said here. E to the natural log of m is m. So e to the natural log of 5 to the x is nothing more than 5 to the x, and so these two statements are equal. Now, let's use a law of logarithms that we surely remember. That is, if we have the logarithm of something to a power, that power can be written as a coefficient in front of the logarithm. So we'll write this as the derivative with respect to x of e to a power, and we're going to write the power as x times the natural log of 5. That's using laws of logarithms. Well, let's go a little bit further then. We know how to take the derivative of e to a power. It's simply e to that power. Okay, it's e to that power, so e to the power x times natural log of 5 times the derivative of the power. So it's the derivative of x times natural log of 5. Now here's a little observation, that natural log of 5 is just a constant, like a 7 or a 1/2 or a -5. So this is really like a 5x, although we have it written backwards. This is a coefficient times x. And so when we take the derivative of a coefficient times x, we certainly just get the coefficient. Like we were taking the derivative of 3x, we would get 3. So here we have e to the power x times natural log of 5 times simply the result of this derivative, which is only the constant natural log of 5. Now we have one more thing to do before we have actually calculated this derivative and written it in the form we want, and that's to recognize, let's go way back, e to the power x natural log of 5 is the same thing as e to the power natural log of 5 to the x. And we just discussed that e natural log of 5 to the x power is simply 5 to the x. So this whole expression is no different than just 5 to the power x. So 5 to the power x is, the derivative of 5 to the power x is 5 to the same power times the natural log of the base that we have here. And we might summarize that a little differently. Let me write here. Let's just kind of state that a little differently now that we've got this information. That if we have the derivative of some constant, in this case not necessarily a 5, any constant, to the x power, then the result we'll get will be that same constant to that same power, but then times the times the natural log of the base, this constant right here. And that kind of summarizes it. Now we also have a chain rule version of this. Let's look at the next slide. Kind of a summary of what we know about the derivative's exponential function. That is, derivative of e to the x is simply e to the x. But the derivative of some other constant other than e to the x power is that constant to the same exponent power times the natural log of the base, the a. Or the chain rule version, the derivative of e to the u is e to the same power times the derivative of the power. Well, if we have the derivative of a constant to some u power with respect to x, this u is some expression in x, then it's exactly the same a to exactly the same power, but then we have to multiply with the natural logarithm of the base, a, and then also multiply with the derivative of this exponent. We'll look at a couple of examples here. Okay, here we have a function that has a base other than e, but it is an exponential function. It's 2 to the power 3t, and we're supposed to find the derivative f prime of t. So let's see if we can remember. I don't have it written here, but let's see if we can remember how we do this. Let's see. Okay, the derivative f prime of t of some constant to a power will be the same constant to the same power. So we'll have exactly the same expression here, but then we multiply it with the natural logarithm of the base, and in this case that base is 2, so times the natural logarithm of 2, and then we have to multiply it with the derivative of the exponent. Of course, in this case it's the derivative with respect to t of the exponent 3t. And of course we know that result is 3, and so we might rewrite a little bit and we might say, okay, this is, we'll put this result 3 in front, so it's going to be 3 maybe times the natural log of 2, all of these are constants, and then finally times 2 to the power 3t. Well, as we've seen in most cases, we can apply this new information with old rules. We can still use old rules along with these new rules. Here we have the function y is equal to x times 4 to the power 3x, and we're supposed to find dy dt. Here I hope that we'll recognize, because we've seen this kind of thing so many times in the past, that we actually have a product of two functions, x and 4 to the 3x. And so to do this problem, to do this derivative, we actually need to use the product rule. So we have the derivative of y with respect to x, that's the derivative we're going to find, will require the product rule, which says take the first function and multiply it with the derivative of the second function. Well, in this case the second function is 4 to the power 3x. And then add to that the second function, which is 4 to the power 3x, times the derivative of the first function, And of course this first function is simply x, and so we know that derivative is 1 very easily. But as we go further, we understand that to find the derivative of an exponential function 4 to the 3x, it will be certainly the same expression, 4 to the 3x, but then we multiply with the natural log of the base, so that's the natural log of 4, and then we multiply also with the derivative of the exponent, and the derivative of 3x is simply 3. And of course over here, as we said, this is just 1 in this position, so we just have 4 to the power 3x times a 1. We go back to the beginning here and we notice that we can probably combine and reorganize. We'll write this as a 3x times the natural log of 4, and then finally times 4 to the 3x power. And then don't forget we have plus 4 to the 3x power in this position. Now, as we've discussed previously, that there's no reason we can't leave this answer. There's a perfectly acceptable answer. But sometimes we're asked, or sometimes it's necessary, to do some factoring. So let's recognize that 4 to the 3x appears twice here. So we could factor in both terms, that is. We could factor 4 to the 3x out, and we would have 3x times natural log of 4 plus 1, and that quantity multiplied with 4 to the power 3x. Either of one of these answers would be acceptable in a problem of this nature. Well, I thought you might find this little bit of information interesting, since we've been talking about exponential functions, and particularly most of our emphasis was on e. And notice, of course, I'll let you read this and just contemplate what it says, but certainly it's talking about transcendental numbers. E and pi happen to be transcendental numbers. There are many others. Those are irrational numbers, but a transcendental number is also one that is not a solution of a polynomial equation with integer coefficients, as opposed to the square root of 2, which is irrational but not a transcendental number, since it's the solution to the equation x squared, is a solution to the equation x squared minus 2 equals 0. So that keeps square root of 2 from being a transcendental number, because it's the solution to a polynomial equation with integer coefficients. And the interesting point is that e was proved to be transcendental in 1873, as you see, by a French mathematician. And pi was proved to be transcendental not too far after that, 9 years later, by a German mathematician. And a little bit of interesting note here, not only that they're transcendental numbers, but the proof that pi is transcendental showed conclusively a long unanswered question about the squaring of a circle. And the squaring of a circle is a problem that was proposed in ancient times, over 2,500 years ago, about whether or not it was possible to construct a square that has exactly the same area as some given circle with only using a compass and a straight edge. And it's not clear here why, but proving that pi was transcendental put to rest forever that no, we cannot square a circle, that we cannot do this by given only a straight edge and a compass.